This video started out as a short piece on loop antennas. I wanted to throw something together on the bench and demonstrate how loops are easy to build and how they can dramatically improve AM broadcast band reception. Well, that idea got torpedoed. Computing the inductance of a rectangular piece of wire is more complex than I realized, and the calculation doesn't match up to the measured value of inductance very well anyway. There are other issues which we might go into in future videos, but I learned along the way that theory only gets you into the neighborhood of the needed values of L and C. To build an effective loop, you've got to experiment. Well, with that realization, I began thinking about the basic physics of receiving loop antennas and the voltages that one might expect at the loop terminals, which you should be able to measure directly. That's how this video came about. So, let's get started. So let's start by thinking about the physics of broadcast band antennas, transmitting antennas. You have a transmitter that delivers an RF voltage to an antenna that generally a quarter of a wavelength high, or at least is electrically, and then grounded. And the conductivity of the ground, or the ground radials, is such that the second half of the dipole is completed by images down into the conductive earth. So you have current, that is electrons, being driven up and forth in this vertical antenna, and that creates a magnetic field. And depending on instantaneously the direction of the current in the antenna, you have a magnetic field, a B field, that is perpendicular to the antenna, the directionality given by the right-hand rule. So the current can produce a field, a magnetic field that is either clockwise or counterclockwise when viewed from the top of the antenna, depending on the time. So the vertical antenna produces an electric field that is perpendicular to the Earth's surface and a magnetic field that is parallel to the Earth's surface. In a radio, if you have a loop of wire, conductor, that is oriented such that the B field flows through the surface defined by the plane of the loop, that will induce a current in that conductive loop. And this is called Faraday's law of induction. So a time-varying B field produces a time-varying current in a loop. So the question that I'm asking is essentially, what magnitude of voltage can we expect to be delivered into a load connected across that loop from the magnetic fields generated by nearby or local AM radio stations? And so the answer to that is given by Faraday's law. In mathematical form, that law states that the voltage in the current loop will be proportional to the number of loops that the length of wire defines times the time derivative of the magnetic flux through the loop. And actually in Faraday's law there's a negative sign here that has to do with the directionality of the current and Lenz's law and things like that, but we're going to ignore that sign in the calculations that follow because we're not interested in the sign, we're interested in the magnitude of the voltage that we measure. What this corresponds to is asking the question of what is the flux phi. And we can think of this as an integral over the induction field B dotted into a differential area that, when added up over the surface that is defined by that loop, gives you the flux. So you can think of this in general as, some current loop, not necessarily circular, and the vector element of differential area, dA, is given by just a small element of that area, so maybe that, and the direction of that vector quantity is normal to the plane or perpendicular to the plane of that loop. All right. So that integral now just becomes the B vector dotted into the vector that's the unit vector that's perpendicular to that surface times dA. first of all, I should say that the B field is oftentimes informally called the magnetic field, but it more formally is known as the magnetic flux density, or as I called it earlier, the induction field. What's known as the magnetic field is actually symbolized by H. And the relation of the two, they're equal to one another to within a factor of the magnetic permeability. And in this case, we're talking about the permeability of free space because it isn't really that much different here at the surface of the Earth. If we were talking about a magnetic medium, then there would be another factor of magnetic permeability of that medium multiplying mu naught. But anyway, the point here is that B is equal to mu naught H. So that integral simplifies now. So we started off with Faraday's law, V equal n d phi dt. But d phi dt is just going to be the integral of b dot n dA. So we take the time derivative of that. And when we convert the induction field into the magnetic field, we introduce a factor of mu naught. All right. So far we've just kind of talked about a lot of integrals, but how do you actually compute those? Well, in the case that we're interested in, those integrals simplify a lot by realizing that at these frequencies and wavelengths and the sorts of sizes of loops that we're talking about, the magnetic field is uniform through the area of that loop. So H is approximately a constant, and it can come right outside the integral, which is over space. So if H is constant in space, it doesn't contribute anything to that integral. So we're left with V being mu naught n d by dt, H cosine of theta from the dot product, and then the integral of dA. Well, that's just going to be the area of the loop, which we'll call A for a moment, and it will depend on the geometry of that loop. If it's circular, that will be pi r squared. If it's rectangular, it will be length times height, so on and so forth. And we're left with this. So the voltage is going to be these prefactors. Notice there's a directionality prefactor that has to do with the orientation of the loop with respect to the magnetic field, and then times the time derivative of the magnetic field. Okay. But the time derivative of the magnetic field at a given point in space is just oscillatory. It's a sine wave. So h of t is equal to some amplitude h naught times sine of 2 pi f, the frequency of the wave, times t. And the derivative of the sine is the cosine, and then it brings out this factor of 2 pi f out in front. And so what we're left with is V is equal to this expression right here. And that looks complicated until you remember that we're not interested in the time variance of this. We're just interested in the peak value. So the peak value of cosine of anything is just 1. And so that leaves us now with a fairly compact formula that expresses the physics of the situation quite succinctly. So V peak here is going to be 2 pi mu naught times n times A, area of the loop, times the frequency, times h naught, the amplitude of the magnetic component of the EM wave, times cosine of theta. And the physics in this is as follows. The cosine of theta reminds us that the direction of the loop with respect to the transmitter matters. This is why you can use loops for direction finding. The size of the loop, the area of the loop, matters, and the length of the wire in the loop matters. All right, so just delving into that a little bit further, and I promise we're going to get to a demonstration here very shortly. Theta is the angle between the magnetic field and the plane of the loop. And so when that angle is 0, you'll have the gain of the loop being maximum. When that's 90 degrees, you'll have it being 0. When it's 180 degrees, you'll have it being maximum again, and 270, 0, and so on. So the loop is most sensitive when the station's antenna is in the plane of the loop in the plane of the loop. All right? And then so finally, if you make a rectangular loop, which I did, you get the area of that rectangle. It's just the height times the width. And you have the following expression for the voltage at the terminals of the loop. Well, we know everything here except for H naught. So, what is H naught? Well, you could actually estimate H naught by measuring the voltage through a loop. And that's not what I'm going to do today, although it's just, a simple division. What I'm going to do is, because I'm interested in estimating the magnitude of this voltage, is I'm going to estimate H naught. And it turns out that broadcast engineers design radio stations so that they produce an electric field for local AM stations that is in the range of 1 to 50 millivolts per meter. And for more distant stations, it tends to go down into the tens or hundreds of microvolts per meter. So, what does that buy us? Well, what that buys us is that we know that there's a relation between the magnitude of the magnetic field and the magnitude of the electric field in a traveling electromagnetic wave. And they're related by a factor of Z naught, the impedance of free space, which turns out to be 377 ohms. So we can just simply divide the electric field that we read out of the handbook by the impedance of free space to get an estimate of the magnetic field. Notice the magnetic field is going to be 2 orders of magnitude less than the electric field. We can actually estimate very roughly now the magnitude of V for a loop or several loops of wire due to nearby AM radio stations. And when you do the math, it turns out that for local radio stations you should expect voltages in the neighborhood of several millivolts, and for more distant radio stations, the magnitude of tens of microvolts. Now, there's a big asterisk there. And the asterisk is that if you have local stations that are actually quite nearby the loop, the receiving loop, then this 5 millivolt number could be, a factor of 10 or more higher. So, does the physics work? Is that true? Well, let's see. So what I've done is I've taken a spool of wire and I've wrapped it around a bookcase. So over here is a tuning capacitor which is not currently in the circuit. I'll get to that in a moment. Here is, let me zoom in on that a little bit, my terminals that are connected here with alligator clips. And I've just wrapped it around a bookshelf, and you can see here the wire goes up to that corner and then across and then down, right, and then across the bottom and then back up, and I do that 6 times. So there's 6 loops of wire. The width of this is about 0.76 meters and the height is about 1.9 meters. So that's the geometry of my loop. And I'm going to show 2 things. I'm going to show, first of all, just the voltage that you measure directly out of that loop, so without a capacitor in the circuit. And then I'm going to show how that can change when you resonate the loop with a variable capacitor. Here we are on the digital oscilloscope. And you can see I've got the time base set so that you can see an envelope, that is to say a modulated sine wave going across the screen. And the amplitude of that wave is peak to peak, it's about 400 to 500 millivolts. And you could convince yourself, if you look at this long enough, that the signal is modulated by a human voice. Now, I don't want to infringe on any broadcaster's copyrights, so I'm not going to do what I'm about to describe. What you can do is you can measure the voltage by an oscilloscope from a loop antenna without any capacitor in the circuit. and then tune across the radio band. This works particularly if you are in an urban area where you've got several broadcasters. And for several of the AM stations, you will see with your eyes how the voices correlate with what you see on the oscilloscope. But it won't be a perfect correlation. Sometimes when an announcer pauses on a radio station that you're listening to, you will see modulation in the signal on the oscilloscope. And the reason for that is because we have no sharp resonance in the loop antenna as it's currently constituted. Or to make that even more clear, the signal that we're seeing on the oscilloscope is actually the sum or a superposition of signals that are radiated by all the AM radio stations in the area. So in my case, I think just by tuning across the band, this is the result of at least 4, if not 5 or 6 radio stations in the market at my location. This is like a radio party line, if you will. This is a very broadband receiver that we're seeing with our eyes, not our ears. Although you could easily hook a diode up to this and make a crystal radio where you would hear multiple radio stations at once. Now, before I move on and make this resonant, I want to do one thing. So I'm going to pause the video here. And what I want to do is I want to show the frequency domain of this signal. Here we are. You can see the time domain up here in the upper part of the oscilloscope display. And we've got the frequency domain down here. This is just the Fourier transform, or the FFT, the fast Fourier transform of the time domain signal above. Each of the major divisions on this scale is 500 kilohertz. So this is 500, this is the bottom of the AM dial. This is 1 megahertz, this is 1.5, and the next little small division there is 1.6 megahertz. These pips correspond to the strength or the energy carried by signals of the different frequencies. They change in time because those signals are modulated, and so that will be the energy that a carrier is bringing along to the loop, and then it changes, the energy changes as that signal is modulated. So you can see that in my area we've got a very strong signal at 1.6 megahertz. In fact, that is true. You can tune that in my location. We've got something at just less than 1 megahertz, and in fact there's a signal at 980 kilohertz, so that's what that is. And then there's some other signals that we're going to be very interested in today. There's a signal here and here, very close to one another, and it turns out that those are at 570 and 630 kilohertz. And then there's another one right about here at 780 kilohertz. Okay, so now what I want to do is put a capacitor in the circuit so that this becomes a parallel LC circuit, and we'll be able to tune the capacitor. The capacitor will be a variable capacitor, as we saw in the opening shots, and we'll see how that changes the spectrum here. Alright, so you see how the time series signal across the top of the oscilloscope has changed, and you see a little bit how the RF spectrum on the bottom part of the screen has changed. So what I'm going to do now is I'm going to start changing the capacitor, and watch the upper part of the oscilloscope, and we'll see that it increases right about there. And you can see that this is clearly an amplitude modulated wave. You can see that one component has spiked in the Fourier transform in particular, much more than all the others. So let's detune the circuit now and look at the spectrum. All of the stations seem to have peaks that are more or less equal to one another. Some are taller than the other, but they're not radically dissimilar. But now as I start adding capacitance to the circuit, and I hit my first resonance there, you see this one spike right there peaks, and that's the spike at 580 kilohertz. 570, 580, I forget which the station actually is. Now, let me turn the Fourier transform off so we can get a better picture of the time series signal. So you can absolutely see how we've preferentially picked out the one signal at 570 kilohertz, and that is the modulated carrier wave, the modulation being due to the audio signal fed in the microphone in the studio. Again, I'm not going to tune the radio in, but it's very striking to see the correlation of what you hear with your ears with what you see on the oscilloscope. But now let's go back to the split view and sample it so that we get better frequency resolution. Watch that large spike here. Watch the amplitude of that go down as I move the resonance higher in frequency until I reach right there. You can see that there's this second spike right there, just slightly higher in frequency, and that's at 630 kilohertz. So we've moved the resonant frequency of this tank circuit, that is the loop antenna and the capacitor, higher, and you saw the upper trace, the time trace, grow in amplitude. Again, we'll just turn off the Fourier transform function and change the time base, and there you can see the amplitude modulated signal of that one radio station. And that's clearly a single signal. You don't have multiple voices modulating that signal. Okay. Now, I only have enough capacitance in this circuit to increase the capacitance now until we pick up our last resonance here. Okay. And now you can see that the spike has gone over to here, and that's at 780 kilohertz. And that is a station that is very nearby my location here. And I won't change the oscilloscope display to show that like I did the previous two stations, but I think this makes the point that you can make a filter that can preferentially identify stations both by looking at the maximum amplitude of what the loop picks up in the time domain and by maximizing the spike of the different station signals in the frequency domain. And finally, here now is just a screenshot of the signal of the 780 kilohertz radio station. Got the time base fast enough that you can see the carrier wave, and what looks like noise is actually the changing amplitude, the instantaneously changing amplitude due to the audio signal that modulates the circuit. If I change the time scale now, you can see an envelope emerge, and this looks, much more like what you normally see. So go down, there's 630, and go down even more, and there's AM 570. Well, I encourage you to try this on your own. This is very simple to do. If you have wire and a variable capacitor and an oscilloscope, of course, You don't need a digital oscilloscope to look at things in the time domain. You do if you want to look at the Fourier transform or look at signals in the frequency domain. But this is pretty neat. So I encourage you to do this and to also play the radio along with the visual display on the oscilloscope. It's pretty neat. I hope you found this interesting. If you did, please give it a big thumbs up below. And as always, thanks for watching.